Happy day to all. Today we are going to see previous year questions in operation research. Let's shall go. Yes. The first question is in an simplex table, if corresponding to any negative j, all elements of the column are negative or 0, the solution under the test is. So whenever in the simplex table, the column is negative or 0 value, the solution is called as an unbounded solution. Okay. The next one is the optimal solution of the following assignment problem using Hungarian method. So Hungarian method, they are given that a person A, B, C, D is there, and then 4 assignments are there. So which assignment to give which person, then it will be feasible. So we have to find out it. So for this Hungarian method, choose the smallest element in a row. So in this row, 8 is the smallest element. So subtract it from all the elements in that row. So okay, 8 minus 8 is 0, 26 minus 8, that is 18, and 9 and 3. Okay, and then for B, the 4 is in the second row, 4 is the smallest element, right? So you have to subtract from the 4. So 9, 24, 0, 22, and then for C. So which is the smallest element? 15 is the smallest element, right? Here. So you have to subtract 15. So 15, the 16, 17, 18 is the answer. 15 plus 8, 15 plus 8, 23, right? So you have to write 23 and 15, 19 minus 15, that is equal to 4, 18 minus 15, 3, 15 minus 15, 0, and then go to the D row, that is a 4th row. This is the smallest element, 10, right? Subtract from all the elements. So 19 minus 10, that is equal to 9, 26 minus 10, that is 16, 24 minus 10, that is 14, and 10 minus 10 is 0. Okay. So now we have to check whether we reach the feasible solution or not. Okay, so in your first column, in your first row, you got a 0, and in a second row, you got a 0, and in a C row, you got a 0 here, and D row also you got a 0 here. But this 2, and we have to check the column also. In a column, you can able to see a 0, but in this column, okay, in a second column, we don't have a 0, right? So that is here, only in this column, we don't have a 0. So that is, we have to degenerate this solution again. Okay, that's why they are calling as an degenerate. So I have to degenerate this solution. Okay, subtract the smallest element from the row, and then similarly subtract the smallest element from the column. So if you are subtracting 0 from all the column elements, you will get the same thing. So here you don't have a 0, so you have to subtract it from 4. Okay, so the second step is, so 0, 9, 23, 9, this will remain as it is, and then 4 you have to subtract, 18 minus 4, 14, and 20, here it will 0, and then 16 minus 4, that is equal to 12, and then 9, 0, 3, 14. So here you have a 0 is the smallest element, so you will receive as it is. So you get it. So now you do an allocation. So how will you do an allocation? So this is A, B, C, D. So in this row, wherever 0 is present here, so I am allocating A person to the first job, and for B job, I am allocating wherever 0, I am allocating 3. Okay, I am allocating A for first job, and for a B for third job, and for C, so C you can able to see in this row, you can able to see that 2 zeros are there, here also on 0 and here also on 0. So that time just hold it and go to the next one. So for D person, you can able to see here you have only 1 0. So here you have a 1 0, you can choose that. So after choosing this, you remove this column, right? You are removing this column. After choosing that row or column, you are removing that, right? So if you remove this column, the C we can allocate 2. So C for 2 and D for 4 job. That's it. So we reach the solution. So A is 1 and B is 3 and C is 2 and D is 4. 4. That is available in the option B. So this is a Hungarian method. Okay. The next question, in a linear programming problem, suppose there are 3 basic variables and 2 non-basic variables. Then the possible number of basic solutions. So for this you have a formula. So that is n factorial divided by m factorial into n minus m factorial. Okay. N is total number of basic variables. That is n equal to basic variables plus non-basic variables. So how much of basic variables are 3 and non-basic variables are 2. So value of n is 5. That is equal to 5 factorial. So divided by the basic variables are called as m. So the basic variables are called as m. So m factorial, that is 3 factorial, and then now n minus m factorial, that is 5 minus 3, 2 factorial. Okay. So 5 factorial divided by 3 factorial into 2 factorial. So 3 factorial, this 3 factorial will cancel, right? So 4 into 5, here 1 into 2 will come. So if you remove this, 2 5s are 10. So option C, 10 is the answer. The next question, the initial basic feasible solution to the following transportation problem using Vogels approximation method is. So in this Vogels approximation method, we have to find penalties, right? So penalty 1 and penalty 2, like that. So what is the method is, the first step, choose the first 2 smallest elements difference, and then same, choose the first 2 smallest element in column. So first we have to find out in row, then we have to find out the difference in the column. So that is called as a penalty. So in this first row you can see 1 minus, here next smallest element is also 1. So 1 minus 1 is 0. So before that we have to see that supply and demand should be equal. Okay. So then only balanced and feasible, and then only we have to go to the next one. So 50 plus 30, 80, 80 plus 20, 100. Here also 40, 30, 70. Here also we are getting the 100. So it is feasible. So next go to the penalty. So here 1 minus 1 is 0, and then 1 minus 2 is 1, and then here 4 minus 4, 2. Okay. First 2 smallest element in a row. Difference between the first 2 smallest elements. Okay, first 2 smallest elements is, here it is 2, here it is 4. Okay, 4 minus 2, that is equal to 2. So in the same way we have to find out for the column also. 1 3 is the first 2 smallest element in that column, right? So we have to find out the penalty is 2, and then here it is 2 and 2, that is equal to 0, and here this is 1 2, that is 1, and 1 minus 4, okay, 1, that is 3. So now you have to see which is the highest penalty. Which is the highest penalty? The number is 3 is the highest penalty. So now I choose what? So this is the highest penalty. So first this is 2 0 1 3 and 0 1 2. This is the highest penalty. So in this we have to see which is the highest value. So 3 is the highest value, right? So in this 3, in this column we have to choose the smallest element. So here it is 1 is the smallest element. 1 is the smallest element. Okay. So for 1 I have to allocate. For 1 I have to allocate the demand and supply. We have to choose the demand and supply. Okay, not the penalty. So 10 I have to assign here. So 10 I am assigning here, this becomes 0, and 50 minus 10, that is equal to 40. Okay. So after allocating wherever 0 is present, so this column will 0, you just strike out this column. So once you assign, you strike out this column. Okay. So this is finished now. Now we have to find out the penalty. So 1 minus 3, again this will be 2 only, this will be 0 only, and this will be 1. Okay, and here 1 minus 1 is 0, and 2 minus 3 is again here also 1, and here it is 2 minus 4, that is also 2. So now you can choose the highest penalty. So here it is 2 and this is also 2. So you can choose any one penalty in this column. So I am choosing this or this. So if you are choosing this, in this row you have to find out the smallest value. So in this smallest value is 2. Okay, if I am choosing this, this is the smallest value, or you can also choose this, no problem. So if I am choosing this 2, and what happens? So 20 I am assigning here to 20, so this will become 0 and this becomes 20. Okay, and so now this row is completed. Just strike it out. Okay, and the next step is we have to do the same thing. See the difference. So 1 minus 3 is, now the penalty is 1 minus 3 2, 3 minus 2 1, 1 minus 2 is 1, and this is third time I am checking. So 1 minus 1 0, and 2 minus 3, this is 1 only. So now we have to choose the highest penalty. So here 0, 1 and 2, 1, 1. So which is the highest penalty? 2. So in that we have to choose the least element in that row or column. So least element is 1. So I am allocating this demand here 20. So it make it as 0 and this make it as a 10. So 30 minus 20, that is equal to 10. Okay, so which is became 0, this column. So just strike out this column. Okay, just strike out this column, and now we go to the same thing. So here it is 2 and 3. Now you see the difference, that is 1 only, and then 1 minus 2, this is also an 1, and 2 minus 1 1, and 3 minus 2 1. So all are 1, right? So you can choose any one. So you can choose any one. So I am taking just the least element. Okay, so for 1 I am allocating 10. So this will become 0, this will become 20. Okay, so now you can allocate for this 20 and 20 here. This row is completed, right? And then now this is 3 and 2, here 20, 20 and here 40. So the allocation has to come like this. Then only your work is correct. So this 20 will become 0 and 20 0. So this will become 0. Okay. So now what are the allocations are there? x11. This is x11. x11 equal to 20. This is an this considered as a matrix. x11 equal to 20 and 13. Okay, x13 equal to 10. Okay, and then x22, this is a 22 location, I am assigning 20. x22 location is 20, and x23 location, that is equal to 20, and x24, that is equal to 10, and x32, that is equal to 20. Okay, so this is the optimal answer. This is the answer, right? But in this option they are given x11 20, x13 10, and x22 20, and x23 20, x24 10, but x32 they have given 10. So this option is, there is no option is correct. So only for this value they changed, right? So the option is none of the above. The option is none of the above. And if dual has an unbounded solution, then its corresponding primal has no feasible solution. If there is an dual or primal problem, if it is an unbounded solution, then its corresponding primal has no feasible solution at all. Okay, unbounded solution, then its corresponding primal has no feasible solution. In the same way, if the primal has an unbounded solution, then its corresponding dual is also no feasible solution. Okay, we have to remember this is a set of properties for allocation. The next question, how many solutions do the following equation x1 plus x2 plus x3 equal to 11 and where x1 is greater than 1, x2 is greater than 2, x3 is greater than 3. So for this question we have to remember some formulas. So x1 is greater than 1. Okay, I am just generating a new one. So x1 equal to x1 plus 1. So this assigning. So x2 dash equal to x2 plus 2. x3 dash equal to x3 plus 3. Okay, so now apply this equation here. Right? Yes. Sorry, here it is dash, I think. So x1 dash plus 1 plus x2 dash plus 2 plus x3 dash plus 3 equal to 11. So x1 dash plus x2 dash plus x3 dash, that is equal to 11. Here 3 plus 2 plus 5, 3 plus 2, 5, 5 plus 1, 6. If 6 come this side, 11 minus 6, that will become 5. So the reverse, the regeneration equation is this. Okay, this is a regeneration equation. Okay, the regeneration equation is this: x1 plus x2 x3, that is equal to 5. So for this equation I am applied here. Okay, so I am assigning for x1 in the place of x1 dash plus 1, and x2 equal to x2 dash plus 2, and x3 is x3 dash plus 3. So I am assigning here, that is equal to 11. So if you add the constant values, 3 plus 2 plus 1, that is 6. If you take that 6 this side, 11 minus 6, that is equal to 5. Okay, this is a regeneration equation, or this is called as an OR value. So OR is 5, and m is number of variables. So here how many variables? x1, x2, x3. There are 3 variables are there. So the equation is m plus or minus 1 and or. Okay, so this is the formula. So m value is 3 plus 5 minus 1, then 5. So 8 minus 1, 7, 5. So 7C5. So this is called as a 7C5. If they ask value, you can find out 7C or n factorial divided by r factorial, n minus r factorial. You can find the value also, but they asked only this up to this. So option D, C of 7, 5 is the answer. The next question is, at any iteration of simplex method, if delta j is j minus cj corresponding to any non-basic variable xj is obtained as 0, the solution under the text is alternative solution. In a simplex table, if there is any corresponding any non-basic variable that is xj is obtained as 0, then it is called as an alternative solution. A basic feasible solution to a m origin n destination transportation problem. Okay, m origin and n destination transportation. M origin and n destination transportation problem is said to be dash if the number of positive allocations are less than m plus n minus 1. So if this allocation, positive allocations are less than m plus n minus 1, then it is called as an degenerate. Okay, so if the allocation is less than m plus n minus 1, then it is called as an degenerate solution. For example, consider this 3 row. Okay, if I'm allocating something here and then something, so this is number of rows. Okay, rows, columns. So number of rows is 3 plus 3 plus minus 1. Okay, this is the formula. So it is 5. Okay, m plus n plus, so 5 allocation, right? It should be if it is lesser than 5. Okay, this is, I did only 2. So 2 is less than 5. So it is, I have to do once again. So this is not feasible. This allocation is not feasible, right? So I am degenerating. Okay, this is called as an degenerate solutions. Okay, if the allocation is equal to m plus n minus 1, then we found out the feasible solutions. Then it is called as a non-degenerate solution. Understood? If the value, if you are doing some allocation, after doing the allocation, the value is equal to m plus n minus 1, then it is called as a non-degenerate. No need to again do the allocation. No, non-degenerate, or it is a feasible solution. But if the allocation, if you are doing in a table some allocation, okay, this 1, 2, okay, so only 2 allocations are coming. After that, I am not able to do any allocation, right? So only 2 allocations are coming. So after this 2 is less than m plus n minus 1. That is 3 rows, 3 column minus 1. So if 2 is less than 5, then it is called as an degenerate. A basic feasible solution to a m origin n destination transportation problem is said to be degenerate if the number of positive allocations are less than m plus n minus 1. So this is also a theory, okay. The next, the total transportation cost in an initial basic feasible solution to the following transportation problem using Vogels approximation method. So the same thing here also, you have to find out the difference and penalty, and then you can able to see the answer is 80. Okay. Shall I do, or you will try now? So okay, I'll do. So 4. So in this row, what is the first 2 difference element? First we have to check the total of supply and demand. Okay, 6 plus 4 plus 8, 3 8 is 24 plus 6, that is 30. But here 12, 8, 20, 34. Okay, so this is not unbalanced solution. This is called as an unbalanced solution. So if it is unbalanced, what we have to do? We have to add one more row. We have to add. So in a column only it is missing, right? So we have in a column, I have to add 0, 0, 0, then put 4 here. Understood? So this solution is an unbalanced solution. Okay, when you count the demand, this is 30, and when you count this, it is 34. Okay, so we have to add 4 in this column. So in a column, you can add a dummy row, dummy column, that is, it became 4. So now you apply the same rules and regulations which you are already done for Vogels approximation method, and apply it and multiply the allocations, you will get the answer 80. If an artificial, the next question, if an artificial variable is present in the basic variable of optimal simplex table, then the solution is called as an infeasible solution. So artificial variables are present when there are infeasible solution is present. If there are feasible solution, we no need to introduce the basic variables or surplus variables or anything, right? So if the solution is infeasible, then only we are presenting the basic variables. The next question, an optimal assignment requires that the minimum number of horizontal and vertical lines that can be drawn to cover all zeros to be equal to the number of rows or columns. So if there is a table, a person A, B, C, allocating job 1, 2, 3. So if I am allocating here, okay, so if the 0 is there, I am allocating this, and then I am allocating this and this. Okay, for A for job 1, B for job 2, C for job 3. Okay, so the allocation, so number of zeros drawn cover all zeros. So when you cover number of zeros is 3. So it should be equal to the number of rows equal to number of rows or columns. Okay, so this is called as an optimal assignment. This is called as an optimal assignment. Optimal assignment requires that the minimum number of horizontal and vertical lines that can be drawn to cover all zeros be equal to the number of rows or columns. The next question, which of the following is the minimum cost for an assignment problem given below? So remove this. So if this is an easiest one, minimum cost for an assignment problem, you can choose the minimum value. So no need to find any subtraction or anything. So they are asking just minimum cost for an assignment problem. Choose the minimum value in the table. Choose the minimum value in the table, this 2 or this 2. So I am choosing this 2. If I am choosing this 2 means I have to remove this row and column. Remove this row and column. And so after that, so this row and column is removed, right? Now we have to choose the minimum element from the remaining. So from the remaining 4. So I am choosing 4. Okay, after that remove that column and row. Remove the column and row. So now you choose 5, 6, 7, 8. So here minimum element is 5. Okay, choose that element and then remove the row and column. Okay, and then now available is, sorry, did something mistake. So I will tell you again. So choose the minimum value from the table. So 2 is the minimum number, right? So choose 2 and then remove that row and remove that column. And the remaining elements are there, no? That remaining element, choose the minimum value. So what is the minimum value in this remaining element? 4. Okay, so choose the 4 and then remove that row and column. So in 4, this is the column, right? You have to remove this and then remove this column. Remove this row and column. Then choose the minimum element from the remaining. So here it is 5, 6, 7, 8. So minimum element is this, right? So remove that column and row. So what is the minimum? The next one is 6. So the allocation is 2 plus 6 plus 4 plus 5. That is equal to 8 plus 9. That is equal to 17 is the answer. So this may be 19. Okay, mistake. So 17 is the answer. The minimum cost for an assignment problem given below is 17. The next question, if the primal linear programming problem has unbounded solution, then its dual problem will have, then the dual problem will have no feasible solution at all. If it is an unbounded solution, then we cannot find, then we cannot have an feasible solution, right? Yes, the option C, no feasible solution. And I am not aware of this Quincke necessary condition, and this is the answer. So all the above is the answer. The next question, which of the following special cases does not require reformulation of the problem in order to obtain a solution? So if it is an infeasibility or unboundedness solution, then I have to do a reformulation. But if I already find out the alternate optimal solution, I no need to require the reformulation. The question is, which of the following special case does not require reformulation of the problem in order to obtain a solution? So alternate optimality. So if I find out the optimal solution, then there is no need to find out the reformulation, right? Only at the time of infeasibility and unboundedness I have to do the regenerate or reformulation process, right? Okay, so the answer is alternate optimality.